In this video, I'd like to talk a bit about how we can verify that Marlowe contracts behave as they should. I said right at the start when we talked about domain-specific languages that because we're working in a more specific language, we can do more with it. And this is a point where I can deliver on that promise. So the first thing I want to talk about is what's called static analysis. And what I mean by that is that we can analyze the complete behavior of a Marlowe contract, a specific Marlowe contract, completely without running it. It's entirely automatic, so there's no need for users to do anything, and it's exhaustive. It does check every possible path through the contract. And what's particularly nice about this is where there is a problem, we get a specific counterexample. So if the contract can go wrong, we show you a particular way you can get to that wrong state. We show a particular set of transactions which leads you to that erroneous behavior. But the thing to realise here is that this works for particular instances of contracts. So if we think about the zero coupon bond, we said exactly what the start date is and the end date. We've said exactly what the notional and the discount are. So that we have specific numbers in there. But given that it's a real contract as would be executed, we can do this automatic and exhaustive testing. Now, what sort of things can we check for? I guess the crucial property we can check for is whether every payment that the contract should make will be executed properly, or are there ways of executing a contract where a payment can fail? And we in particular, we can, if there is a way that the payment can fail, we can show you a path to that failed payment. So you get it's not just a matter of you guessing how it might fail. We can show you precisely how it can fail, and then you can fix it, or you can live with that potential. Another property we can check for is any payment or deposit in the contract going to be for a negative amount. That doesn't make sense, but the contract may, just because of the mechanics of the way it's been written, have that possibility. We want to be able to check that can't happen. And other properties, perhaps specific to a contract, we could imagine. Does it always result in more money being paid to person one than person two, for example? We can check a number of anything that we can state about the form that payments take, for example, should in principle be checkable. How is this done? What we do is we use what's called an SMT solver. SMT is a more sophisticated version of what's called SAT solving, which is really just exhaustive checking to see whether logic formulas can be satisfied. So simple formulas of propositional logic. But Z3 and SMT is what's called satisfaction modulo theories. So it allows us to do more sophisticated checking with arithmetic. And really what we're doing in checking Marlowe contracts is checking arithmetical constraints. We use the Z3 or Z3 SMT solver, but others could be used. And we have an implementation in the cloud so that it's unnecessary for anyone to install the solver for themselves. So of course that would be possible. And we get finiteness for this solver to work because we know that we know that the contract itself is finite. We know that there are bounds on the size of the state, and we know that there are bounds on the number of transactions, number of inputs we might have, and so we can minimize. We can be sure that this is a finite problem, as it were. It is solvable. The question is not whether it's solvable. The question is whether it can be solved in real time. And our initial implementation was very slow. We used a technology to translate from Haskell, and we've now rewritten that and got a an order of magnitude speed up, at least an order of magnitude. And so now we're getting results back for reasonable size contracts pretty quickly. So that's entirely automatic. This can be push button. You get the you get back from the analysis whether or not a contract can go wrong. So that's one part of the arsenal. But as we said, that's only for this specific contract. We agree in the case of the zero coupon bond, we've agreed the notional and discount. We've agreed start date and end date. So we can do the analysis once those things are specified. But what if we want to prove things in general about templates? What we can do then is use what one might call formal verification. So this is machine checked proof. So it's like writing a mathematical proof, but it is checked for correctness by the program that does the system that we're using. In this case, we use a system called Isabelle. And what Isabelle gives us is, the proof is done, I've said, by hand, in inverted commas, but there's a lot of automation in there. So in many cases, the system can find proofs automatically. And what we've done is we've been able to prove properties of the implementation of Marlowe. So we can prove things about the whole system, as it were. And we could also, in principle, we've not got round to this, but we could prove properties of templates for contracts. So all possible payment schedules. So irrespective of the notional and the discount, irrespective of start date and end date, we could show that the zero coupon bond didn't produce failed payments in the case of a guarantor, for example. But what I'm going to concentrate on here is properties of the platform. And what's we've written our semantics in Haskell, but Isabelle uses a slightly different language. But what if you take a look at what we have here in Isabelle and compare it with the Haskell implementation, you'll see that what we have is pretty much a transliteration, a line-by-line translation of what we have in Haskell. So we've been able to take our semantics, put it into Isabelle, and then we've been able to prove things. And here are two examples. What we're doing, the first theorem here says, if every account in the contract has a positive amount or nothing in it, and we compute a transaction, then the same property is true of the output of that transaction. So each transaction will preserve that property. So if we start off with, typically we start off with no money in any of the accounts, we finish up with only positive amounts of money in accounts. So that's giving a guarantee of how the machine behaves, irrespective of what happens, irrespective of whatever contract we execute. And the second theorem here says, once you've computed the output of a transaction, there's nothing more to do until another transaction is submitted. So the contract is what we call quiescent after we've computed that. Okay, so I think that's those give you some illustrations of the things we can do, that we can automatically verify properties of individual contracts, and that we can in general reason about both the properties of the system and the properties of contract templates. And these are things we get because our language is a DSL. We can talk about all Marlowe contracts in a way that we couldn't talk about all Plutus programs, all general purpose programs. Right, what we're going to do now is take a look at the Marlowe playground, which allows us to put all this stuff into practice.